All right, so in the last video we talked about stress at a point. We were talking about just 2D for the most part now. And this gave us a normal stress component, sigma, and a shear component, tau. This came about from when we exposed the surface. You actually get a complex distribution of the internal tractions. This is the forces, the tractions that the bodies are right, forces that the bodies are left. You can look at each little differential traction. It has a component normal and perpendicular to the plane. Normal and in the plane. The component that's normal to the cut plane, normal stress. The component that's in the plane is shear stress. And remember, all both have units of force per area. Basically taking it to their intrinsic quantity. Materials will fail at a certain stress level, regardless of the geometry. Depends on what's the stress point. That's where the issue is failure. Okay. As I mentioned before, it's usually quite difficult to derive this complex distribution, so we tend to simplify them. And we will concern most often in this class with the notion of average stress. Okay? And this turns out to be a lot easier. Actually, we're going to get the average stress from the internal reaction forces. And the internal reaction forces we mentioned before are kind of easy to deal with because they come right from. Okay. All right. So where this comes about is all right, so let's look at the notion of average normal stress. So I'm going to put a little weight on it, okay? The average normal stress. If you think about it on this surface A, right? That's surface A. The average normal stress on that surface is the sum of the stresses over that surface divided by the surface area. So the sum is really an integral quantity, right? So the integral over the area of the stresses at a point, the normal stresses at a point, differential area. So that's the sum of all the stresses. This is now a force. Force times area times area. And the average is then to divide that by actual area. All right. So this term down here is obviously just the area of the exposed surface. So that's this area. That area, cut area, exposed surface area. Okay, now what about this top quantity? What's that? Well, if you think about that, let's look at simple part and tension. Measure a component like this. And there's maybe an external load here applied to P. This is the cut surface, right? So there's actually another one. Right? But on this surface, we see the internal tractions. Let's just look at the normal ones. They probably have some parabolic distribution. It's the actual stress. Okay? Again, this is force. Well, you know, I didn't mention, I didn't talk more, I should have talked in the last video about the units. Sloppy about that. Force per area, right? If we're in SI units, force per area is a Newton per meter squared, right? That's the basic unit of stress. Now, that is defined as a Pascal. PA is the symbol for Pascal. Now, Pascal is really small. So A lot of times we're not talking about Pascal. A Newton, you think about it, Newton's about the weight of an apple, and a meter squared is like the size of a table. The stress level of an apple distributed over the entire table is very small. Right? Usually, when we're talking about actual loads, right, megapascal and something even gigapascal, we're talking about the strengths of certain materials. Okay? These are more typical units. Mega 26, giga 10. In English units or imperial units, basic unit of force is a pound, and unit of area is an inch squared. And this is called pound per square inch, or you can call it PSI. Now, pound per square inch is a lot more than a pascal. It's about 1,000, more than 1,000 pascals per PSI. You know, I'm talking about 1 pound instead of being on a meter squared on an inch squared, so it's much smaller. A lot of times you'll see still things written in terms of KSI, which is 10 to the third PSI. That's 1,000 PSI, and sometimes people talk about MSI, which is 10 to the sixth PSI, right? A mega PSI. So be careful about the units of lots of practice. Those are the units that we're talking about. Pascals, PSI. Okay? So be clear about KSI as opposed to a kip, right? Kilowatt power, that's unit of force. KSI is unit of stress. All right, so back to this picture. We've taken the tensile test, exposed the surface. Here is some distribution of normal stresses. Now, if you look at this, right, the net force acting on this surface is the internal reaction force N. And so, although from equilibrium we can see that N equals P, we can also see that N has to equal, or it results from, the net effect of all this surface traction. So it's the integral over the area of that normal stress. That is N. So N really is a fictitious thing. The internal reaction force doesn't exist per se, but you can consider it as the combined effect of all the normal stresses acting on the surface. Similarly, V is the effect of all the shear stresses on that surface. So that's N. All right. And now we can immediately recognize that that's actually what's in the numerator here. So that's N. And then that tells us that the normal stress is N over N. All right? The average normal stress is just the internal reaction force at that point divided by the area. Okay? A lot of times N is P, but be careful. When I talk about stress, when I talk about average stress or stress, we always talk about stress at a location, right? At this kind, or so on. You need to make sure that the stress is always going to involve the calculation of the internal reaction forces at that location, not the external ones. They don't emphasize this several times. It's a mistake I see students make a lot. Right. So that is the average normal stress. Average normal stress. You know, we can get the basic approach to getting this is you can get N from equations of equilibrium on the free body diagram. So for example, this was the problem. You get N from the sum of forces, sum of moments. Once you know N, you know this cross-sectional area, right? Again, that area is the cut area, it's the exposed surface area. That's N. And then we can get the average normal stress. Now, the average normal stress, right? Look at it. The surface. The average normal stress is as if there was a uniform distribution. Another way you can kind of think of it. This would be sigma bar. Right? If the actual distributed stress was uniform, then sigma, the stress at a point, would exactly be equal to every point of average normal stress, right? In reality, it's typically not. You know, we might have a parabolic some distribution, right? Called actual stress, right? And you can see what's going on here is at some points we're underestimating the value by considering, well, I should say this. At some points, right here, the average normal stress is actually going to be higher than the actual stress. In some locations, it's going to be the other way. Actual stress might be higher than the average normal stress. I mean, that's the notion of average. Right? Some points are higher, some points are lower. That's an average. Right? So there's a bit of an error that possibly happens here. Or I should say it this way. If you think about the failure of a component, it happens at a point. So really, failure occurs as a result of actual stress at a point. When that exceeds some value, you usually see something of failure. But that's a little tricky to calculate directly. So we usually use the assumption that we're considering actually average normal stress. So this actually can be an underestimation of the actual maximum stress that occurs. Right? We'll talk about it later when we talk about factor of safety. There's something to do to try to compensate that factor. Another thing is also when you have stress concentration, these other things called like stress concentration factors to try and correct for that. Now, we're going to consider geometries where this variation is not that big. And so looking at the average stress is a reasonable thing to do. There'll be some situations where that variation is quite large, and then we'll use things like stress concentration factors to try and compensate for that variation. Okay, so that's the average normal stress. The average shear stress is basically goes the same way if you look at it. Go back to this. Oh. Force like this. All right, and so this produces normal stresses. Now let's just look at shear stresses. There's actually some distribution of shear stresses on that face. You know, again, remember the actual traction. Something like that, right? But there's a normal, and then we're looking at the in-plane component, or the shear component, right? So this is actually tau is a function of position on that surface. Again, the surface we're talking about is this surface here. This is A. Now, the net force acting on this, well, it's opposite of normal convention. That's going to be the integration over that area of tau. Now again, you want to look at the average shear stress. The average shear stress is going to be the integral of tau dA. You can see it's just over the area. That average shear stress. It's similar to the average normal stress. It's just not a component. So we get that. Again, it can be lower than the actual in some locations and also higher than the actual. So E gives us the shear stress and N gives us the average normal stress. Now, from this point on, actually, if I call something stress, most likely I'm talking about the average stress, right? If I mean stress at a point, it'll actually be stress at a point, all right? Okay. Maybe I should just do a quick example. Well, let's kind of redraw this part. So let's determine the average normal and shear stress at this point A. That's this is that sort of graphic. Okay, and let's just do this measure. So let's say this is 100 pounds, call this 50 pounds, and then we'll get here 10 inches. Okay, so in this case, actually I don't think just need those components. So the average normal stress is N input A. Average shear stress is E. So what do we need to know? We need to know the normal component, the shear internal force. There's actually going to be a moment as well, but we don't really need to know that. We also need to know this area. So that's part of the part design. So let's say that this is 3 inches, and then this whole thing is 1/4 of an inch. Okay? So that means the area of this exposed surface here is going to be 3 inches times 1/4 inches. That's 3/4 inches. So 0.75 inches squared. That's the cross section. All right. Now, if we do sum of forces in the x equals 0, that tells us from this free body diagram that N has to equal minus 100 pounds. And if we do sum of forces in the y direction equals 0, here at B, the way I've drawn it, B balances out 50, so B equals 50 pounds. Right? So actually, we have 100 pounds acting this way, and net pound of 50 pounds acting down this way on the face. All right? So this is actually what we would call the compression force acting on the face. Compression force tension force acting on the face. All right. So the average normal stress is going to be at N, minus 100 pounds over the area, which is 0.75 inches squared. So we're going to get pounds per square inch, and this is going to be 400 over 3. So 1.2. So this is 130 psi. Okay. Now, for the normal stresses, it's really important that you get the sign correct. Right? For the shear stress, it's a little more tricky to ascertain the sign. It's not, there's a convention to it. But for now, I don't want to really worry about the sign convention on shear. All right? We'll talk about it. I'll do that later. This is fun. The shear is going to be 50 pounds over the 0.75, which is square. Right? So then it's going to be 4 times 50 over 3, so 4 times 200 divided by 3. That's like 70. 73.3 psi or something like that. I'm actually really terrible at these things. I should be better at it. Oh, I got this one. Oh, 66. obviously it's half of this. Okay. But anyway, that's the value, right? So that's the average normal and the average shear stress.